That is good to know. No line. I like no line. It's not Dancing Ghost Coffee. Yeah. I guess it just depends on the situation, but I'll have to check that out. They'll let you have the pods for free, huh? Wow. Sweet.
And you get your own cup for free.
And your own cup. That's a good deal. Free is a great deal. Okay. Electronic elements. Lecture 1-6. We now review a few lumped parameter elements for electronic systems that are all going to be familiar to us. Okay? So actually this lecture is like completely review of electronic elements, but we're doing it in a way that is parallel to how we introduced the other elements. And then on Friday, we're going to tie up the ends and see, oh, look, they all have parallels. Okay, that's the plan. So I marched through in the same formulaic way. Let a current I and voltage V be input to a port in an electronic element. Since for electronic systems, the power into the element is the product of voltage and current, we call the current and the voltage power flow variables. Voltage is always understood to be between 2 points in a circuit. If only one point is included, the voltage is implicitly relative to a reference voltage called ground, right? The magnetic flux linkage, lambda, which is a quantity that I think we talked about in passing a while ago, is the integral of the voltage over a period of time. Similarly, the charge is the integral of the current over a period of time. We now consider two elements that can store energy, called energy storage elements, an element that can dissipate energy to a system's environment, called an energy dissipative element, and two elements that can supply power from outside a system, called source elements. So our first energy storage element is the capacitor, which has two terminals and is composed of two conductive surfaces separated by some distance, as we know, right? One surface has charge Q. Oh, I froze up there. That's weird. Has charge Q, and the other negative Q. A capacitor stores energy in an electric field between the surfaces. Let a capacitor with voltage V across it and charge Q be characterized by the parameter capacitance C, where the constitutive equation is that the charge is proportional to the voltage by constant of proportionality C, the capacitance. Capacitance has derived SI unit farad, where a farad is an amp second per volt. A farad is actually quite a lot of capacitance, so we'll typically talk about it in terms talk about the capacitance of capacitors in terms of micro, nano, and picofarads. The time derivative of this equation yields the voltage-current relationship, what we call the elemental equation for capacitors. dV dt equals 1 over C times I, which is dq dt, right? The time rate of change of the charge. Resistors have only algebraic IV relationships, so circuits with only sources and resistors can be described as algebraic or by algebraic relationships. The dynamics of the circuit with capacitors are described with differential equations. So now we've got this whole differential equation entrance that we had before, right? So same thing. Capacitors allow us to build many new types of circuits: filtering, energy storage, resonant circuits, blocking circuits, bypassing circuits. Actually in this week's lab, you guys are using a capacitor that is effectively a filter. So you're using it as an RC filter. And what that's doing is filtering out high-frequency components from your signal. And it's passing through low-frequency components. So what that tends to do is smooth out a signal. So I know that we haven't talked a lot about the energy or the frequency domain. You guys probably have an instrumentation more. So in your 315 class, you guys probably talked about it to an extent at least. So the filtering aspect of the capacitor is the aspect we're using in that lab. We're filtering out high frequency stuff, giving us a smoother, kinder, gentler DC signal, right? Okay. Capacitors come in a number of varieties, with those with the largest capacity and least expensive being electrolytic, and most common being ceramic. The one you guys are using this week is electrolytic. There are two functional varieties of capacitors, bipolar and polarized, with circuit diagram symbols shown in figure 1.9. So you guys have seen them, but this is good to remember. Bipolar, polarized. Polarized is the one you guys are using this week. Because electrolytic, I'm about to say, are all polarized capacitors. So yeah, polarized capacitors can have voltage drop across in only one direction from anode to cathode, otherwise they are damaged or may explode. Electrolytic capacitors are polarized and ceramic capacitors are bipolar, like several of my relatives. Okay, so what if you need a high capacitance bipolar capacitor? Here's a trick. Place identical high capacity polarized capacitors cathode to cathode. What results is effectively a bipolar capacitor with capacitance half that of one of the polarized capacitors. So polarized capacitors, since they're electrolytic, tend to come in much higher capacities, right? Capacitance of an electrolytic capacitor tends to be on the order of, several orders of magnitude, oftentimes larger. So if you want a large bipolar capacitor that won't get damaged, you put them cathode to cathode, and you can effectively come up with you lose half of your capacitance when you do that. So if one of those capacitors has capacitance C, when you put them together, they actually have capacitance C over 2. So kind of like you lose some, but it's still much, much greater than what you can get with a typical ceramic capacitor. So it's a nice little trick. So I always tell this because what we'll typically use it when we're trying to measure something is as a filter, and a lot of times you want more capacitance to filter it more aggressively. Okay, and if you're going to, you could design a higher order filter, but if you want to just get away with a simple RC filter, you probably need a big capacitor. But if your signal is a signal that goes negative ever, then you have to have a bipolar capacitor, so you're sort of stuck. And that's why I put this in there, because it's a nice trick I've used on several occasions, so I always pass that knowledge on. Don't forget this is possible. There's actually there's a funny internet debate about it too, on like electronic stack exchange, and people argue about it, and it's a good time. But I've tried it and it does work. So. Inductors. A pure inductor is defined as an element in which flux linkage, lambda, the integral of the voltage, across the inductor is a monotonic function of the current. An ideal inductor is such that this monotonic function is linear, with slope called the inductance L, i.e. the ideal constitutive equation is that the magnetic flux linkage lambda is proportional to the current with constant of proportionality L, which has units of inductance, SI derived unit Henry, H. But, of course, most inductors have inductance best represented in millihenries or microhenries. The elemental equation for an inductor is found by taking the time derivative of the constitutive equation. d I dt goes in, and then d lambda dt is just v, so we'll just put in v. So d I dt equals 1 over LV. Inductors store energy in a magnetic field. it is important to notice how inductors are, in a sense, the opposite of capacitors. A capacitor's current is proportional to the time rate of change of its voltage, and inductor's voltage is proportional to the time rate of change of its current. So it's a dual relationship there. Inductors are usually made of wire coiled into a number of turns. The geometry of the coil determines its inductance, L. Often a core material, such as iron and ferrite, is included by wrapping the wire around the core. This increases the inductance. Inductors are used extensively in radio frequency RF circuits, which we won't discuss in this text. However, they play an important role in AC to DC conversion, filtering, and transformers, all of which we will consider extensively. Although we aren't going to use inductors in our AC to DC converter, you can use them. We're using like a relatively straightforward way of doing AC to DC conversion. You can get more exotic than what we're doing, but it works. The circuit diagram for an inductor is shown in figure 110, which was up here. This guy. If you guys don't recognize the inductor symbol at this point, you got some problems ahead of you. So, I don't know if that sounded like I enjoyed that, but like that was not the intention. I hope that you all recognize the inductor symbol, and I support you as students, no matter if you do or you don't. Okay, resistors. Resistors dissipate energy from the system, converting electrical energy to thermal energy, i.e. heat. The constitutive equation for an ideal resistor is Ohm's law, V equals IR. This is already in terms of power variables, power flow variables, so it is also the elemental equation. Here's the resistor circuit diagram symbol, and I'm not going to make any snarky comments this time. Sources. Sources, aka supplies, supply power to a circuit. There are two primary types, voltage and current sources. Ideal voltage sources supply an ideal, or supply a voltage that the user specifies, independent of the circuit to which it is connected. So you set it to 5 volts, and it's 5 volts no matter what you connect it to, right? All it must do in order to achieve this is supply whatever current is necessary. Ideal current sources, on the other hand, provide exactly the current a user specifies, independent of the circuit to which it is connected. All it must do is to supply whatever voltage is necessary. But of course, that implies that they could supply infinite power, and as we know, we can't do that. So if we want to do modeling real sources, we can make this nice little variation. So no real source can provide infinite power. Some have feedback that controls the output within some finite power range. So these would be what we've been calling regulated supplies, right? So our myrios, the analog outputs, have regulated supplies within a certain power range, right? Like it can't provide very much power at all. So once you try to ask it for very much power, the voltage that it's providing isn't really the voltage that you're telling it to provide. Also, the benchtop DC power supplies that we've got in the lab, those are regulated as well, but they have power limitations, much higher power than the myrio, but at some point it can't provide it anymore. An example of the type of sources that don't have this regulated aspect or feature to them are the function generators. So you guys have been using function generators as well. Function generators are not regulated. I've never seen one that is regulated. And they are therefore best modeled in this sort of real source way. So if you have a regulated supply within the power range that it's spec'd for, you can treat it as an ideal source. If you're going to either leave that power range or you're going to have an unregulated source like a function generator, then you have to model it with this sort of real source model. So many voltage sources, for example, batteries, do not have internal feedback controlling the voltage. When these sources are loaded, when they're delivering power, they cannot maintain their nominal output, be that voltage or current. We model these types of sources as ideal sources in series or parallel with a resistor, as illustrated in figure 112. Most manufacturers specify the nominal resistance of a source as the output resistance. So here is a voltage source in series, an ideal source in series with a resistor, making it a so-called real source or a power limited source. And similarly for the current source, you put a resistor in parallel. What this does effectively is limit the amount of current that can come from the voltage source and limit the amount of voltage that can come from the current source. So that's the effect of the resistor. And for the function generator, it's 50 ohms. So we had a discussion about this. It really comes down to the extra credit problem on the midterm exam. Most people didn't attempt it because it was a long exam. But it was asking about this very thing. So if you've got this source and you've got an output resistance of 50 ohms, and you're going to go across some load, right? So I'll call this RL, and I'll call this VS. So the function generator, you set it to some voltage, right? So say you set it to 5 volts. On the screen, it says 5 volts, right? So your screen says 5 volts. We're ignoring amplitude or peak to peak here. I'm just going to assume we're doing an amplitude. You can some of them talk about it in peak to peak, some of them talk about it in amplitude. So that's a different consideration. When we're thinking about this, like think about these oscilloscopes the function generators that we have. We set it to 5 volts, and we expect 5 volts to be delivered, but we know that it's an unregulated supply, so it has to be assuming some specific RL, okay? So the standard one that most function generators assume is 50 ohms, okay? So that means that if you've got your voltage across RL, then it's a voltage divider, right? So you've got RL divided by RL plus 50 times VS. And if RL is 50, this is 50 over 100, or 1/2 VS. So that's the typical function generator assumption, is that you're going across 50 ohms. So what it does is its internal VS, if you set it to 5 volts on the panel, it'll actually be 10 volts. That it's going to assume you're going to put it across a 50 ohm load, so it's going to give you what it assumes you're going to need. Now, we very rarely do put it across a 50 ohm load, right? So if we put it across a high impedance load, so if RL is, instead of 50 ohms, is large, then this is large over large plus a little bit, which is effectively 1, right? And the VS is what we actually see. So this would be, so equals VS. So if we put it across a high impedance, which would be if we connected it right up to the function, or to the oscilloscope, instead of connecting it to some circuit. If we just connected it right up to the oscilloscope typically has a high impedance to it, right? So you're going to read 10 volts on your oscilloscope, even though you said 5 volts on your function generator. If you put some other load here, then you're going to get something else. So your voltage is going to depend. You have to take this into account when you do your circuit analysis. So this is some of the issues that I've seen in the analysis and the lab reports have come from this, a little bit of this confusion. That's part of why I put this as a bonus question on the midterm exam. A nuance to this is that our function generators, most of them, the newer ones, they're fancy, okay? They have a fancy setting where it's called the high Z, high impedance setting. And what that does, as far as I can tell, is it just says, okay, instead of assuming 50 ohms, we're going to assume it's a high impedance load. And if you say 5 volts, we'll put 5 volts here. So that's my understanding of the high Z mode. I'm actually, I should put this, I'm confident that it effectively works that way. I don't know if there's any other like cool thing you can do with high Z mode. I think that you can go to higher voltages if you use high Z mode, because if you ask it for 5 volts, it doesn't have to give you 10 volts now, it only has to give you 5. So it's really just like, you don't gain anything, it's just like imaginary that it like actually gains. There's another setting on the oscilloscopes that I've seen some of them get into, and I don't know why they get, people just probably accidentally do this, but you can put in an attenuator, like a 10x attenuator on a cable going into the oscilloscope. Say you're trying to measure a really large voltage, and you know that your oscilloscope can't go to that high of a voltage, so you put a 10x attenuator on the cable. The oscilloscope is smart, and it has a mode where it says, oh, do you have a 10x attenuator on here? If so, then go into this 10x mode, and every voltage that we measure, we're just going to multiply by 10 and read it out as 10 times. So the 10x attenuator is canceled out from the reading, which isn't really getting you anything. It just makes it look, you are able to measure higher voltages, but you have to have an attenuator, so there's no real gain in the amount of voltage you can measure. It's just a nice way of presenting it. And I have mixed feelings about these modes because they generally just cause confusion, and they don't really actually have a lot of benefit other than that. So be cautious of that. I've seen them get into that mode on accident. Actually, when I went in there, I was trying to measure some voltage, and it came out to be like 150 volts, and I was like, whoa, that can't be right. And I went in and I found that it was in like a 10x mode, and then I was like, okay, that makes sense. Yeah, I was like, what scale is this? And then I was like, no, that can't be right. Yeah. Okay, I'm gonna stop rambling now and let you guys